Hello everyone. Today is the first lecture in a many-part lecture series to get you to fully understand the fundamentals of static mechanics. Today we will be looking at equilibrium conditions. The lectures will be split into multiple parts such that you can easily find out what's important to you. We will start off today with the most fundamental force summations. So in static mechanics, equilibrium is required. The general form for equilibrium is that the sum of forces is zero and the sum of moments is also zero. This condition states that all forces and moments balance. This ensures that in our system, our 2D system, that it does not tend to move to a certain direction because there's an unequal balance of forces or moments. Okay? And the way that we would write this is sum of forces is equal to zero and sum of moments is equal to zero. Okay? And in 2D statics, the forces that concern us are my forces in the x direction and the y direction, and my sum of moments in the z direction. The first element we will encounter in mechanics is known as a truss, and a truss is usually indicated by a symbol like this part. So a truss is very unique in the sense that it can only take axial forces. What this means is it can only take forces in the direction of the truss itself. In other words, this direction. It cannot take forces perpendicular to it in this direction. This is very important. And now how do we connect trusses with one another? We have to use supports and joints, okay? So supports are to connect trusses with the environment, and joints are to connect trusses with one another. So there are a couple very key and important types of supports, and I will introduce everything to you right now. So first one is a one value support, okay? One value support is indicated like this. This is the same thing, but at an angle, or allows for translation in a different direction. So in this first support here, this support allows for a translation in the x direction and also allows for a rotation in the z direction. Okay, so it allows for this movement and allows for this rotation. Okay, what is hindered is this movement. Okay, and this one is very similar. So this one allows for movement in the y direction and a rotation in the z direction. Okay, but does not allow for a movement in the x direction. So those are the one value supports. Now we're going to encounter two value supports. This is one of the most common types of supports. It's very important. This is known as a hinge joint or just a standard two value support. This support hinders both types of translations but still allows for rotations. So this only allows for rotations in Z. Okay, and this is a different type of two value support. We can see this one is different from the previous ones because it doesn't have the ball here, right? So in this type of support, we only allow for translations. There's no rotation allowed here, okay? This is a translation in X is allowed. Lastly, we come to three value supports. So three value supports are another very important thing. This is known as a clamp, and this restricts everything. So this bar right now cannot move at all, okay? There's no movement. None of this is allowed, okay? Perfect. And now we go on to joints. So joints is another very, very important topic, and it is how you connect two elements to each other. This is a truss, this is another truss, and how do we connect them together? We have to have a joint, okay? First type of joint here is known as a shear joint. Shear joints allow them to shear up and down from each other, okay? So this allows for a translation in the y direction. The second type is known as a normal joint. This can move like this in the x direction, so it allows for translations in the x direction. Importantly, it can only move outwards from each other and not into each other, okay? And lastly is the most important and most common type you will see is known as a rotary joint. So a rotary joint allows for these two bars to rotate independent of each other. Okay, it's the most important type that we will encounter the most frequently. So now I will introduce to you a force summation. So for force summations, all you have to do is add the required forces, like add all the forces in your required direction. And this always has to sum up to zero as long as your system is static. To solve for forces, all you have to do is take any arbitrary direction as positive and define all your forces from that point onwards in the other side. And very importantly, for basically every mechanics course that I know about, you always define tension as positive and compression as negative, okay? So here we will look at this sample question, which is a very, very simple case of how to do a force summation. First thing I have to do is take a free cut because I'm trying to figure out the truss forces 1 and 2. So I have to freely cut out 1 and 2, and that gets me this system here, okay? With this one as, of course, element 2, and this one as element 1. And as I said, tension has to be defined as positive. So after my cuts, I have to have my arrows which indicate my forces pointing out of the bars, okay? Pointing out of the truss. Very important. So now I see that I have two forces and I'm trying to solve for them. And I've been introduced to the vertical and horizontal sum of forces. So which one makes more sense right now? It should be the vertical sum of forces, because I have S2 and S1 both pointing horizontally, but S2 is the only one that has a vertical component, right? S1 is perfectly horizontal, so it doesn't have a vertical component. So if I take sum of forces vertical, I only have S2 in my equation. So then I can solve for S2. So sum of forces vertically is going to be 0, right? And for now, let's just define upwards as positive. Again, it's arbitrary. So S2 points up. The component that points up is sine 30 degrees, right? Minus F, negative because F points downwards, and that has to sum to 0. Again, we have a static system. Static systems are in static equilibrium, so it equals to 0. So sine of 30 is 1/2, so it's S2 times 1/2 is equal to F. S2 is going to be equal to 2F. So now that I'm given S2, or now that I've solved for S2, I can now take the horizontal sum of forces to figure out S1. Sum forces horizontal. Let's take right side as positive. Again, this is arbitrary, has to be 0, static equilibrium. So S2 points to the right. Its horizontal component is cosine of 30 degrees. Minus S1, so S1 points to the left, so it's negative, has to be 0. Cosine of 30 is square root 3 over 2, so I know that S2 times square root 3 over 2 is equal to S1. S1 is going to be equal to square root 3 of F. Okay. If you want a bit more clarity, S2 can be substituted in with the previous result. So that's how we get square root 3 of F. For moments, the summation is a little bit different. So moments describe a rotational force. The moment is always equal to a force multiplied by its perpendicular distance to your reference point, okay? This distance is often referred to as the lever arm. So the moment the force generates is very heavily dependent on what your reference point is because of the lever arm's distance being able to change, okay? So a very simple real-world example to prove this is to use a door, okay? So imagine if you're trying to push a door. And if you push somewhere like here, very close to the hinges, you're going to have to push with a lot of force in order to move the door, right? This is compared to if you push all the way at the very end or close to where the doorknob is, then you can use a lot less force to push the door open. This is simply due to the moment that you generate. So when you push close to the hinge, this is your lever arm right here, right? L1. And this is much smaller than your second lever arm if you push at the second point. So the moment you generate is much, much less, and hence your force has to be higher. Okay, so remember, moment is a force times a lever arm. So your lever arm being shorter implies that your force has to be much larger. That's why all the doorknobs you ever see are always going to be as far away from the hinge as possible. Okay, this is just so you can push the door open easily. And it's very important to note that moments are actually induced when a force travels a perpendicular distance to a point. So a force that does not travel perpendicular to your hinge will never generate a moment. So for example, if you try to push a door in this direction, you will never be able to open it, okay? This does not induce a moment. So a very common exam trick that you might encounter is where you're supposed to take moments such that you only have one force in your question, and therefore you can solve for this unknown force, okay? So we will use the most standard case there is, which is this system right here, where I have a 2-value support at A and a 1-value support at B with a force that's smack in the middle. Okay, this is the most standard case. So first thing we do is we take a free cut because I'm trying to solve for the support forces, as you see. So I need to have the support forces in my question. I cut away my two supports and I end up with support force AV, AH, and BV. Okay. So support forces you always add in to the movements that are hindered, okay? There is not a force when the movement is not hindered. So for example, B here is a 1-value support and can translate, right? So therefore, there's not going to be a horizontal force at B. And both of these are rotary joints, or have a rotary joint component on top, which means they allow for rotations. Therefore, I will never have a moment like this, okay? This does not appear as long as my rotation is not hindered. So only what's hindered has to be added, therefore I have these 3 new forces. Now, the first force summation I can do is of course the horizontal force summation, right? Since I only have one force horizontal, which is AH. So when I do this summation, I get the AH is going to be 0, okay? We'll take rightwards as positive. AH is 0 because nothing else is a horizontal force. Okay, very simply. Now, afterwards I need to try to figure out AV and BV. So I cannot do a vertical force sum immediately because I have AV and BV both as unknowns, right? So a vertical force sum will just give me an expression with two unknowns. What I need to do instead is try to take a moment somewhere such that one of the forces disappears, okay? In other words, I need to take a moment somewhere where the lever arm of one of these two unknown forces is 0. In other words, I take it at either point A or point B. So I'm going to choose to take it at point A, but you can try taking it at point B too. This is, of course, point A, so I'll take sum of moments. At point A has to be 0, okay? And I will take clockwise as positive. Once again, this is completely arbitrary. So F times its lever arm distance. F is here. It crosses this lever arm, which was L half, minus BV times L is going to be 0. So BV is here. The lever arm it crosses is this distance. Once again, it's always perpendicular distance to my reference point being A here, right? So moments at A. So then I have L. Now, the sign here is what generates a clockwise and what generates a counterclockwise moment. So F crosses this horizontal distance. What I do is I draw my arrow from F's direction, so downwards initially, and it crosses leftwards to get to A, right? So it induces this sort of a rotation. That's why I know it's clockwise. I do the same thing with B. So B points upwards, right? So I'm putting my arrow upwards, and once again it goes left because A is left of B. So it gives me this, which induces a moment in this side, which is counterclockwise, okay? That's why BV times L is negative, and F times L half is positive. So I now can solve for BV is equal to F half. Okay, so now that I've solved for BV, I can take the sum of vertical forces and say that's equal to 0. So now with BV, I only have one unknown vertically, which is AV, right? So I can directly solve for it now. So AV plus BV minus F is going to be 0. AV is equal to F minus F half, the value of BV, right? AV is going to be equal to F half. So please remember to always do your equilibrium condition that gives you only one unknown, okay? Like taking that particular equilibrium condition doesn't actually give you an answer, so it wouldn't make too much sense. Make sure your equation only has one unknown, and then you can set up any equation you want, okay? And as I mentioned earlier, forces need to always cross a lever arm to induce a moment. That's why if you ever see questions like this where you have more than one unknown, you can either take like a point where the force is actually applied, or you can take something perfectly vertical at that point for this vertical force in order to take a sum of moments there such that one of the forces disappears, okay? It's also really important to know that the sum of moments at any single point on a system always have to become 0, okay? It's not just at points A and B that it's 0. I can take it literally anywhere. Every single point always has to have a sum of moments as 0. So you can take it anywhere just as long as it makes sense. If you found this video useful, please like and subscribe to help the video reach more people trying to learn mechanics. If you want to support what I do further, consider also checking out my website where I provide many more exam-like questions that are much more difficult than what I can cover on YouTube. Every task there also contains a video explanation similar to this one. The website is constantly being updated to add more questions that you guys raise. If you want, you can also buy me a coffee on my Patreon with the link in the description of this video. Everything I produce here is done completely from scratch, so these videos take a really long time to make. Thank you.